I just wanted to start with this beautiful picture that I took just to generate some interest before I start boring in between, and then I will show you some of my photographs, and then lastly I will also uh, I would like to tell you something about the light pollutions and the effects that it have, and why we have chosen this Hanle in Ladakh as the place for observatory. So basically, I have I tend to keep it very simple and not go deep to generate some interest for everybody. Okay, right. So this is my next slide. Okay, yeah. So as you can see, this is the image of the observatory with the beautiful Milky Way in the background. I have quoted Ahmed Zaveli, preserving knowledge is easy, transferring knowledge is easy, but making new, these are all fundamental research, and we don't get immediately, whatever we call immediate benefit from the astronomy, because it is a fundamental science. Okay, so this is, my name is Dorje. I'm the engineer in charge, as Arun already introduced. So I'm the engineer at this facility since inception. That was like 20 years back. I joined this institute just after doing my BE in electronics and communication from Surat. I've seen many students have also joined from Surat, so they must be knowing now NIT Surat. So that's where I did my engineering college, and soon after I joined this observatory. That's my connection with Surat. I was just happy to see some people from Surat. That was nice. So the dome on the right side that houses the telescope, that's a 2-meter class telescope. I will come on it later and give more details about the telescope. So this is a place in the Himalayas. It is called Hanle, which is around 270 kilometers further from Leh, towards the Chinese border. We are very much near to Chinese border. Just behind, if you see the front where the stars are rising, the Milky Way is rising. It's 25 kilometer crow flying is our Chinese, Indian and Chinese border. Okay, so this is another beautiful caption that I wanted to tell you, that night hides the world but reveals a whole universe. So this is another interesting image I took of both the light pollution as well as the starry skies in the same pictures. Just minimize my own screen. Okay, I'll just put it together. So you can see on the left side, I stay at Leh, which is the town, and 270 kilometers from Hanle. So on the left, you can see the light pollution and of coming from the city, and then it is we are not able to see many stars here. And then on the other side, with the same shot, we can see very nice starry skies. So that is the impact of light pollution in our life. So most of you must have experienced all that. You're not able to see so much stars in the night. But yes, Hanle and Ladakh is so located that we don't get too much light pollution except for the inner city, but urban areas are like very beautiful with starry skies. So why are we doing? Many people question us, why do we do astronomy? Okay, astronomy basically is one of the oldest science. So as far as I remember, when I was young, so my grandfather used to tell me, oh, that the bright stars, the most bright star has risen, so it's time for our harvesting. So that was like, even in fact our ancestors, they study the stars on the planetary movement to know more about us. So astronomy is a natural science that deals with the study of celestial objects, and it has got lots of historical benefit like time determination. Most of you must have heard about Jantar Mantar. So Jantar Mantar were like historical heritage sites which are actually created to give us the time. And basically, I've visited. You should also visit Jantar Mantar in Jaipur. It gives to the accuracy of 1-2 seconds. One of those yantras. Okay. So astronomical navigation in the sea. Basically, in the sea, you cannot see any landform. So you can navigate with the help of stars. So, and astronomy also accelerated development of mathematics and physics. So I'll come later to it. So, and cosmic research brought new technologies to common life. So, so what have we found? So when 400 years back, when Galileo first started seeing the through his telescope that he's made, so he could see the Jupiters with 4 moons and everything in the universe didn't circle the Earth. So he also found that moon does not have a light its own. Moon has got bays and craters, and moon is not completely spherical as people believe. So there was also a very important discovery that happened in India around during 1868 in one of the solar eclipse that Jensen, a French astronomer, he detected a spatial line at 587.49 nanometer. And then he was like stunned because that element was never found in the Earth at that time. And later on, he named the element as helium. So basically, it is helium is named after, I think, Greek Helios, which means the sun, that the element has come from. So, and as you know, helium is the second most abundant material in the whole universe. So later on, helium was also detected here on the Earth too. And the transit of Venus, when it happened in 2004, so it was used to measure the exact distance from the Sun to the Earth, which is 1 astronomical unit and this much kilometers. And during the same transit of Venus, that was in 70,000. In 2014, the transit of Venus was used to measure the dip in the intensity, which was tested, and later it was used in Kepler missions, and it was used. And Kepler mission till date must have discovered around 4,000 and more exoplanets. So basically, astronomy has a lot of benefit, but it does not have a direct impact. But then there are a lot of spin-off. So nowadays, everybody has got a CCD camera in a mobile. So the CCD camera was first used for astronomy, getting astronomical images, and now, as you can see, it is in everybody's pocket, and everybody just carries it. Because of that discovery, everybody carries the camera and in the mobile in their pocket. And the Kodak technical pan film, originally created by astronomers studying the sun, is used extensively for medical and industrial photographer and artists. And in 1977, John O'Sullivan developed a method to sharpen images from radio telescope, which is now implemented in wireless networking. And whenever you go outside, nowadays you find a lot of X-ray screening machine, and the X-ray screening machine that was first made. This technology was made for X-ray observatory, and then later now it's everywhere, on airports, on railway station, everywhere. And the aperture synthesis used in MRI and CT scans was first developed by radio astronomers and Nobel laureate Martin Rayl. So General Motors used the astronomy programming language ideal to analyze data from car crashes. The fourth, that is that's a software which was developed for a telescope, is now used by FedEx to track packages. And as you know, all the mobile nowadays have GPS satellites, to measure the distance to some accuracy. So all these GPS satellites, they rely on astronomical objects such as quasars and distant galaxy to determine the accurate position. Okay. So this is now this is a general question. I don't know. I wanted to make it interactive, but I think maybe because of short of time, still you can give the answer in the chat. Do you know how much time does the Earth takes to complete one rotation on the axis? So this was like I thought it would be more interactive, so I can just see some answers. Hold on, I raised the hands. So sorry about that. Okay, right. I'm seeing some answers. 86,400 exactly. Okay, there are two things. 86,400 is the solar day. So that is the solar day, but the exact thing is the C answer, which is 86,164. How I will tell you here. So basically, that 86,164 is actually the sidereal ray, which is based on the star movement, while as the 86,400 is the solar day. So basically, we use 86,164 because of the accuracy to the stars to track, to compensate for the rotation of our Earth and to track a star so that it does not move away. Because as you know, otherwise the Earth rotate on its axis, stars are stationary. So in the background, you can see one of my images which has got star trails. Basically, the stars are not moving, but it's because of the Earth rotation that we can see star trails. This image was taken for around 1 hour when it looks like the star has moved for a sufficient distance. This is the pole star. Pole star is actually around 45 arc minutes away from the actual pole. Okay, this is the, so the star, in layman's sense, we can say the star has risen from here to here or here to here for the duration of the exposure that happened here. So basically, one simple example we can have is the equatorial mount, where we align our telescope with our polar axis, and then we move only one motor, and then this is called the equatorial mount. So this is the most simplest kind of telescope that one can make, but the accuracy of the polar alignment should be very good, so that we can keep the star. So this is the example of the equatorial mount. So when the star is here, so it will slowly only one axis move, and it will track this one, this one, this one, and then it will keep on tracking the same stars. This is the polar star. You can see this axis of the mount is parallel, or you can see straight to the pole star. So this is the same imaging. But what happens, there is a disadvantage with the equatorial mount, is that it becomes very bulky when the telescope becomes bigger. So with the advent of modern computerized system, it has become easy to make alt-azimuth kind of telescope that is mostly used here. These are other type of telescope. So nowadays, most of the telescope are alt-azimuth mount. So whatever we have at the Hanle observatories, alt-azimuth telescope, where the altitude is 0 to 90 degree, 0 to 90 degree, and azimuth 360 degree, it can move. So it can track any star. So okay, why Hanle? Yeah. So so the next stop we choose Hanle for going for making the observatory there. So one of the few reasons is that Hanle Observatory is located at around 4,500 meters above sea level. So you can just imagine it's 4.5 kilometer above sea level on the in the atmosphere. So there's more clarity of the stars, how we see that. And because we are located in such a region, we are completely what do you call, bounded by the Himalayas, which acts as a defense system, and they don't allow the monsoon clouds to come here. So most of the nights are clear here. So like, for example, we have two types of monsoon, as you know, western disturbance, which comes in winter from the Mediterranean Sea. And then most of the snowfall happens in Kashmir area, etc. And only because we are still further away east to Leh and 500 kilometers from Srinagar, so most of the light cloud passes, and the night sky is clear here. And the other monsoon we have, whatever we are receiving right now in the plains. So what happens? Most of the rainfall, whatever happens, they get dropped at the Himachal, Uttaranchal, other areas, and only light cloud passes through, so which gets clear in the night. So that's one of the reasons why we've chosen Hanle. And the other reason that we have chosen Hanle is that, like, when it was installed, it was the world highest observatory, but right now it's the 8th highest. But in terms of, I think it's second in terms of world highest optical and infrared observatory. So the other two location best telescope was either in the Canary Island in the west or in Australia. So there was a like 90 degree. So we could feel a huge gap. So when it is daytime in Hawaii or other places where the most of the major telescopes are located, so it will be night here, and we can follow any transient event happening. So that is one of the reason why it was chosen. And the third reason is lower moisture in the atmosphere. Now, this is a very important factor. So what happens when you are higher altitude, all the starlight it comes and it doesn't get absorbed by the moisture. So that makes you can see more star here because the starlight is not absorbed. And this is one of the best site for infrared observation. So infrared lights coming from stars gets absorbed in the moisture. So if there are more moisture, so we infrared rays cannot reach the Earth, and hence we cannot do infrared observation in any other parts of India other than the higher altitude region. So that is why one of the reason, and we have good transparency. I mean, good transparency is that. So I have a small story which is associated me when I first joined this Hanle Observatory, which is called the Indian Astronomical Observatory. So when I got selected, one of my aunts, she was telling, "Oh, you got selected at that place. Oh, there the distance is so much that you never tend to reach it." So basically, only later I realized that because the transparency is so good, you can clearly see to any object which is like 10 to 15 kilometers. When you start walking, you will never reach there. So that is the best thing. And that is another reason why Ladakh is a paradise for photographers. So basically, the transparency is so good that the frame gets filled up. So you can see clearly all the mountains in the background and even the foreground, whatever object you want to have. So that is one of the reasons why Ladakh is also good for photographers also, and it is a heaven for photographers. So they are saying like Ladakh अगर जाओगे तो एक कैमरा तो बनता ही है. So do bring your camera because anybody can be a photographer here. So and low light pollution, which is the most important factor that we have, is that is why we have chosen this place. We are very far away. Leh town is 270 kilometers far away, and this is the darkest region in the whole of India. So in India, what happens actually, 90% of our population actually cannot see a Milky Way because of all the light pollution. So, but now I'm seeing some more awareness that people want to bring down their lights and would like to see more stars as their ancestors or their fathers, grandfathers used to see. So that is one of the major reasons that we went. All the major observatory are going to remote locations so that there is no harm because of light pollution. So and the other thing is that we have got we get in the 365 days we get spectroscopic nights for 260 per year. That is means very few clouds passes, and then we have photometric nights. That is zero clouds. We get around 190 days per year. And our seeing is 0.9 arc second. Seeing in layman terms can be like, you must have seen that the stars twinkles. Basically, star doesn't twinkle. It is because of the atmospheric refraction. So when the starlight comes, reaches us, it goes through many refractions. So it forms whatever the as you have seen refraction when you put a spoon inside water in a transparent water, it bends. So because of the bending, we feel like the star is twinkling. Basically, which is not. So that is why we have got very good seeing of 0.9 arc second and uniform distribution of useful night around the year. And the other factor is good accessibility. Basically, from this 270 kilometer stretch, that there are no passes in between which gets closed And so that's what this longitudinal advantage I told Hanle is actually the other two major observatory when it was installed was either in the east 90° and 90° west. So this is the photograph of the 2-meter class telescope. That is our main telescope. So the primary mirror, which is situated here, the diameter of the mirror is 2 meters, and which is the heart of the telescope. Actually, it takes around 3 years to polish, grind this mirror. And these are the so what happens? There's this concave type mirror here, sitting here, and the light from faraway stars, they come as a parallel rays, and then they get reflected on. This is the secondary mirror, and then this is further reflected down. This is called the instrument cube, and here we have a lot of instrument which I will describe slowly. So one of our main instrument is HFOSC, which is the Hanle Faint Object Spectrograph camera, and there are other TIRSPEC, which is the infrared Tata Institute of Fundamental Research infrared and imaging spectrograph camera, and we have got high resolution spectrograph camera that is mounted, and the astronomers, they can use any of the instrument in a matter of 1 minute. They can change their instrument to the starlight. So this is the spectrograph which I was talking, which is our main instrument. This is used for this. This is the camera, CCD camera, and here when the light comes through, we have got a folding mirror which is here. This is a folding mirror I have not shown here. That's a collimating lens and the prism, and this is the camera lens, and this is the camera that is sitting here. So what exactly is inside here? For if you want to do imaging, you have to only put all the filters. That's all. But when you do spectroscopy, then there's a thing called prism, which is actually a combination of prism, as you know, which gives us our spectrum, and then some gratings. So we use this prism to get the spectral lines and to know what the material is constituted in the star, whether it is a metallic star or a gaseous star. So that can be found out from this instrument. So its wavelength is the optical wavelength 350 to 900 nanometer. So the detector is a 2048 by 4096 pixel CCD, and the pixel size is 15 by 15 micron, and we have got nine prisms. This is an UV-VRIs and scientific filters and other filters. This the CCD camera that you can see, they have to be actually cooled with the help of a liquid nitrogen, which we have a plant there, and every day this camera is cooled down to -100 °C, and it is maintained at that temperature with the help of a liquid nitrogen. As you might be knowing, the liquid nitrogen temperature is around -192 degrees. So those are this, and this is the similarly we have, this is the TIRSPEC, the Tata Institute of Fundamental Research spectrograph, as well as this imaging camera. So we have a similar setup here. We have got prism wheel, filter wheel here, and then the light coming. This is the CCD. This is light coming from the telescope, and then it is through a folded mirror. It is given to the prisms, and then it is imaged. So we have some 16 filter location and 5 prisms. Okay, coming to the what we do there. Actually, now if you can see in the toggle, there is a certain bright star that has come up. This is actually a supernova explosion that happened in 2004. It's called the 2004 supernova, 2004J. So this was discovered by a telescope that it suddenly got brightened up in 2004 January or March. Here it is. Why am I not seeing? So this SN 2014J is a type 1A supernova. So basically, this is the one of the closest supernova that we have seen in recent year, and it's very significant. And we can know all the interstellar medium in this is the M82 galaxy. So it happened here. So that was imaged through, and this was followed by all the amateur astronomers too, because it was quite bright. So and then this happened, and this is one of the other supernova SN 2013 AB. So basically what we do is like when we do imaging through the telescope, we follow the light curve. This is called the light curve. So basically the light curves tells the it gives the intensity, and it tells how it's decaying with each filters, and with time. Like this is the time. So it was actually followed up for around 365 days, 1 year. So how it's the light curves is decreasing, so that is studied, and the spectra, as I told, it determines how the luminosity and brightness and color of a supernova evolves and varies with time. So that's what we find with this imaging as well as spectroscopy. So this is another example of image that has been grabbed. So it's an example of spiral galaxies. The arms of are usually thin. Basically, you must have seen better pictures on the internet, because those are like taken by amateur astronomer or through NASA, which are actually with different filters. So here we have got only scientific filter to study all those things. So it may not be very beautiful for a layman person who wants to see very exciting supernova. This has been these are all taken to our HCT 2-meter class telescope. So this is another spiral galaxy, and this is around like 125,000 light years away, and is located and is receding from us at 3747 kilometers per second. Has a bright core and a blue spiral arms, shows many star forming region. Asymmetric type indicates it's a gravitational distorted. No interacting companion is not. Why it is like why the asymmetric shape is there. So that still has to be found out. And this is the other facilities that we have. This is the growth India telescope. Basically, growth is a global relay of transient telescope. Watching transient happened. So this is a collaboration with IIT Mumbai. IIT Mumbai has has PhD in astronomy also, and even in I think graduate courses. So this is a robotic telescope, which is Alt-Azimuth, and the aperture size of the telescope is 0.7 meters. So this is completely robotic. So it can be used from IIT Mumbai, or it can be it can take images by itself by putting the files in scheduler mode, whatever the events that needs to be observed through the telescope. And this image I've taken. So this is, and so you can see this is the core, and this is the dark force nebula. So, and I think this was Jupiter around that time, and this is the Scorpius constellations showing around. And this is the core of the Milky Way. You can see. Okay, so the other thing is that we have a few smaller and very big telescope that is coming up. This is like since 2007 or 6. This is called the Hagar telescope, Himalayan high altitude gamma ray telescope. Basically, this is a collaboration with Indian Institute of Astrophysics and Tata Institute of Fundamental Research. And here we have 7 telescopes, each with 7 mirrors. So each of this telescope has 7 mirrors in a total area of 4.4 square meters. These are used to study the gamma rays. Basically, we cannot directly study gamma ray, but then the Cherenkov effect that happens in the atmosphere when the gamma ray interacts with it, that can be studied. So that is studied here. And this is the MACE telescope, which is called the Major Atmospheric Cherenkov Telescope. This is being installed by Baba. It's nearly installed. It's so the total effective aperture call is like 21 meters. So it's a very big telescope. For comparison sake, you can see a truck head. So this is such big. So this will be the largest gamma ray telescope in the, I think, northern hemisphere. And this will be commissioned soon, and they will be doing observations with it. And we have the other object, this telescope called National Large Solar Telescope, that will soon come up at Meerut. So here it's an artistic impression, but the rest of the image is, because this telescope is still not here. So rest of the image is of the beautiful Pangong Lake that we have in the north east of Ladakh. So here we will have this 2-meter class solar telescope. This will be used entirely to study the sun, and it will provide a front-ranking international facility on Indian soil. It can resolve 50 kilometers on the sun, and it can see a magnetic field dynamics of 50 kilometers resolution, can understand the flare and coronal mass ejection better, can understand the sun-earth connections. So the other thing, as I told you, I'll give you a simple example of planetary motion, how it affects and how. This I've simulated from the software called Stellarium. You must have heard about it. Here you can simulate, even you can the Stellarium, when you download on your mobile, you can watch whatever the what is the sky positions right now. So this is an here you can see this is the dark sky nebula, as I've already told you. So this is Jupiter. So what happens is that if I play this image, I've simulated is from 2007, May 14th. So this was around the certain time. So here, what you can see, the air is changing and Jupiter is moving. Although the Milky Way and all the constellations and the stars, they are at same stationary position. So Jupiter has moved here in 2009. And then further on, it has in 2010, it has completely moved out of its frame. So after the 2011, it was never in that frame. So this is just an example for understanding. As a beautiful, I thought it is beautiful to show it around. So 2012, in fact, it was not in the same frame. So Saturn has suddenly started coming, and Saturn takes longer. You can see Saturn makes smaller jumps each year. 2014, 5th of May 14th, around the same time, 3 a.m. So Saturn is moving slowly, and now 2016, you can still not seen Jupiter. And 2018, suddenly Jupiter came up. Jupiter has, I'm sorry for the disruption. And now you can see 2019, it has come around the same position. So this was used by our astronomers earlier to see the planetary motion. And then like after 2007 till 2019, something like 12 years. So the Jupiter is not actually, it's also circling around the sun, and it takes around 12 years. So this is one of the examples that have. And here, this is a photograph taken by one of my friend Ajay Talwar on the left side. So you can see the actual pictures, and the this one Jupiter is around the dark sky nebula, and the 2019 I've taken a similar image, and it's around the same place. So this is just an example of how planetary motions were detected by our ancestors. So this is what I've shown. So these are some of the images just to give a visual trait that I've. This is the Orion Nebula, and this is the Bernard Loop that is showing. This is Taurus constellation, Pleiades, and this is the bright star Sirius in the same frame. So this is I'm just. It was a selfie shot taken by a timer while I was standing at the observatory. The observatory hill is just behind this house where this hillock ends. So this is so you can see so many stars. In fact, sometimes it gets very difficult to even identify the known constellation because of the large number of stars. So this is the telescope and the surroundings on a moonlit night. You can see because of moonlight, the star intensity has dimmed, but this is the Pleiades constellation. This is the Taurus B type that I showed here. And these are from different focal length, and the shape won't be the same. So this is the, we cannot see the telescope because the dome is not transparent, made up of aluminum sheet. So, but with the help of photography, we can show something more than what our eyes can see. That's an example. So here, as you can see, the slit of the dome is very narrow. It's like around 5 degrees here. So what I did is like that. I took an exposure of 3 minutes. So the dome moved from here to here, and the light kept falling on the telescope. And as you can see, the stars have, because of our rotation, the star has moved from here to here. So it was like 2 minutes exposure, and then in a single shot, we can show the dome as a transparent when the dome is moving 180 degrees from here to here. So this is the Haga telescope, as I've shown. I've already told you, these are the 7 meters each, and then the 7 the 49 meters are there. And this is a winter night sky, and you can see this is our Andromeda galaxy seen here. This is called, these stars are called the summer triangle. It's consisted of Vega, Deneb, and Altair. This is the summer constellation. So in the night, if you just look up, and there will be 3 stars which forms a. Now this is because it is a panorama, so it's a bit skewed. So in the sky, if you just happen to look around 9 o'clock, that's what I remember. So you can see a triangle formed by 3 bright stars. That's called the summer triangle. And this is the core of Milky Way has already gone down. And here, this is a beautiful image where you can see, even in my earlier, the sky is not dark. Basically, our eyes cannot see this greenish, but there is an air glow, which is because of the interaction of the absorption of the sun rays, and then slowly it is irradiated in the night, and then it gives this beautiful air glow in the night, which can be seen. It is something similar to aurora, but on the mid latitude you cannot see aurora. Aurora is actually because of there's a beautiful green air glow that can be seen in the northern latitude near poles, on both the poles, but on the southern side we don't have much because it's Antarctica, not much land around. And then there are a lot of things happening in this image. Like there's this beautiful, this is called the zodiacal light. So zodiacal light actually falls dawn. So sometimes in the middle of the night, you will tend to see a bright triangular shaped light emerging out. So people many times, even at the middle of the night, they think that, okay, the dawn is coming up. But then it is a zodiacal light. I may not be able to tell how it is formed right now, but you can search in the internet, zodiacal light, ZODICAL LIGST. And okay, now more about one of my interests is that light pollution, how to decrease the light pollution. So because you are all students and future generations, I thought I'll just give a small thing. I hope it's too much time. I don't know, if you want to stop, you can stop here also. I didn't follow the time.
It's your call, sir.
Hold on. I just want to see how much. Okay, just see this. So this is 2 images that I have taken just subsequently, and I was very lucky. The next image what I took was like the light went off. You can see this is heavily polluted, the same thing, and this is, you can see the difference, and the air glows, and how much difference it makes when there is no light, and you can see more stars and more air glow. So this is the light pollution effects, and how I will try to go very fast. I think that was too much. So wildlife actually is very harmful for us because for night sky viewing, and it's also a major health issue because it decreases the melatonin production, which is actually responsible for all our recoveries, etc. in the night when we sleep in the dark skies. So light pollution also affects the wildlife. The negative impact on the astronomy. So one single image was taken from 2 different locations, so you can see how much beautiful this one is, and this is through an light polluted sky. So what we can do is last 2 slides. Shield. We can for a good sky we can shield our lights. We don't want light to go up in the skies. We can use timers and motion sensor whenever we require, and we can use lower wattage bulbs, save electricity, carbon dioxide emissions. We can save money. Warmer colored bulbs, develop local partnership, and the most important things is appreciate and enjoy the night sky, teach and share with others. So this is what we can do. We can do star parties. We can see together when we have less light pollution in our own area wherever we are living. Okay, thank you much. Thanks, Arun. That's all.
Thank you so much, sir. I think it was fantastic. You've taken us through a journey of many things today, from teaching us about galaxies to different telescopes, what like instrumentally what telescope consists of, and you've shown us such amazing pictures of night sky which we have not seen in like a lot of time. So Arun, we'll take few questions now. Maybe we have another 10 minutes.
Perfect. So. If Mr. Anshul can actually stop sharing his screen,
okay,
it will allow both of you to come.
Yep, yeah, please.
Yeah, sir, I'm reading through some of the questions, so you feel free to answer some of them. So few of them have questions like, could you please suggest some researchers kids can join hands with so they're asking about if kids can join such things and how they can learn about astronomy. I mean, I think that's what they're asking. They're asking if how kids can help in such research and things like that.
Oh yes, very nice question actually. I will just lower my hand. I think I done it by mistake. I'm sorry for that. Basically, right now I'm hearing a lot of interesting news. Like there are a lot of asteroids being discovered by students. Basically, which is not happening with us because we are like completely the professional astronomers. They have make their proposal to observe through the stars. But there are many telescopes around, and then a lot of kids are actually discovering new asteroids, and that's a very good thing that is happening. And anybody can join. I think with some good research, people can join those study groups, and it will definitely be very good. That's all.
Thank you, sir. So I'm skimming through some of the questions. So there's this interesting question. Do planets introduce some kind of sound when they revolve? So somebody's asking if planets
no, we as far as, because I'm not actually an astronomer, but as far as I heard, no, we have nothing else, nothing else.
Yeah. I don't think there are sounds. So some other questions are like, how can young kids start contributing from home? Could you suggest some activities, research projects, learning groups, something which kids can join, or where should they start if they have to start learning about astronomy or like astrophotography?
What I remember very early, I've seen this. NASA has got a lot of NASA kids. I think the students here will be above that age. But then NASA has got very good page for study material. And what else can I think about?
Yes, sir. I think NASA has like most about all planets, and yeah, I think that's one of the best resources which you've given. There's another question from one of the students. They're asking, what is the benefit of learning astronomy? And can you tell some more activities like this to get more information? So they are asking, what's the benefit of learning astronomy? I think you mentioned in your first slide. Yeah.
Yes. Yes. Basically, it is actually a very interesting thing, I can say, first of all, for everybody to get involved and get educated. Not exactly being, but then there are various opportunities for being professional astronomers inside the country, and a lot of the premier institute all over the India, like IUCA, IIA, IITs. They provide professional courses for students, and obviously there are a lot of job benefits also in all those institutes where they get absorbed also. And then obviously it's for research, and you can in fact discover many things also, because the sky is our greatest natural laboratory, I can see. And the more we study about the stars, we know more about ourselves too.
Thank you, sir. That was like beautifully put. There's one more question from Kanishka. She's asking, what type of camera do you need to use for astrophotography?
That's a very good question. Nowadays there are two things. Actually, the mobile photo camera, some of the mobiles, they have come very nice with all this night mode, where you can expose the sky for 30 seconds, and you can pump up the ISO and have a very good lens. So any of the DSLR cameras or this mobile, which can actually, where we can have this, we can open the aperture for 30 seconds and bump up the ISO to 1600 or 3200, can give a very good, can be used to do astrophotography. And also the most important thing is a tripod, because otherwise in the 30 second it will blur and you won't be able to get. And the aperture has to be minimum like 3.5 or 1.4 you have.
Thank you, sir. That has been one of my interests also, but I always think that astrophotography is like a costly hobby.
No, we basically now we can always get started, isn't it? So agree. That's how you learn. So it can be done from the lowest end DSLR camera with a lens. It can be started off. That's how I did it.